Okay, Maclauren series. It's writing the function as a power series. So rather than writing a function as, say, sine x or cos x or something like that, and then calculating what it is, we write any function like sine x or cos x as a power series. That means it's some constant. So a is constant. A0 represents the first constant and so on. I'll be printing these out, so don't worry about scribbling this out. Let me go at a reasonable pace, and then you can have a look at the notes afterwards. Okay? So A0, A1 is a constant, A2 is a constant. So what we're saying is that for many functions, you can rewrite the function as a power series. In other words, as a series of terms involving a constant, some constant lots of x, some constant lots of x squared, a number of x cubes, a number of x to the power 4s, a number of x to the power 5s, where x is the value. So we can write sine x as some sort of power series. The beauty of that is that when we come to integrate and differentiate, then all we need to do is integrate or differentiate these separate terms individually, and integrating or differentiating something like that is straightforward. What Maclauren's method allows you to do is to work out what these numbers are. We need to work out what are these numbers in front of the x terms, the x squared terms, the x cubed terms, and so on. And that's what we're going to be looking at over the next few minutes. So if our function fx can be expressed as a power series, and many can, we need a way to find the constants a0 and so on, a1, a2, up to an, the nth constant. Finding a0 is easy. If you think about what we've just written here, the power function here, if x is 0, then all of these terms disappear because x is 0, and so the value of the function at 0 will give us a0. So finding a0 is easy enough because at this point all the other terms disappear. If we differentiate the function, here's our function, fx equals a0 plus a1x plus a2x squared plus a3x cubed and so on. What we're saying is we can write this function, it could be the sine function, as we'll see, or the cosine function, in terms of this power series. If I differentiate this series to get f prime x, then a0 is gone, constants disappear. The x disappears in front of the x term, so we're just left with a1. This second term, bring the 2 down, becomes 2a2 to the power x. Differentiate this, becomes 3a3x squared, and so on. Now, if we let the differential equal 0, find the value of the differential when x is 0, again, these terms, any term involving x disappears, and we can find a1. So in the original function, if we let x equal 0, we can find a0. In the first differential, if we let x equal 0, we can find a1. Then what do? We differentiate again, let that equal 0, and that will allow us to find a2, and so on. So to find out what the Maclauren series is, what the power series is rather, for a function, using this method, we just have to differentiate this function over and over again, the function here. So that's what we're going to do. So if we look at it, we find that, and this is going through the general Maclauren now, so there's our original function, a0 plus a1x plus a2x squared and so on. The first differential gives us this, as we've discussed, differentiating the first one. The second differential, note double prime here, means a second differential. Differentiating this, the x will disappear, so we're just left with 2a2. This becomes 3 times 2 is 6, a cubed x, and so on. Now we differentiate again, we get 3 times 2a3 plus 4 times 3 times 2a4x, and so on. Each time we differentiate, we keep bringing these powers down. We know we end up with 4 times 3 times 2, 5 times 4 times 3, differentiating again, 5 times 4 times 3 times 2, and so on. So we end up with this. often. And so a shorthand way of writing that is 5 factorial in this case. 5 factorial means 5 times 4 times 3 times 2 times 1 actually. So we end up using this factorial notation in Maclauren instead of having to write 5 times 4 times 3 times 2 or 6 times 5 times 4 times 3 times 2. We use this notation, the factorial notation. So we end up with a general expression for that Maclauren series. And this is, in an exam, what you'd be given. It's a way of finding out what the power series is. And let's have a look at it. So, it's saying we can write any function, like the cosine of x, the sine of x, as a power series, where a0 is the first constant. The first differential, when x is 0, gives us a1. The second differential, when x is 0, divided by 2 factorial gives us a second constant, a2. The third constant, a3, is the third differential when x is 0 over 3 factorial, and so on. There's a pattern. The next term would be the fourth differential when x is 0, divided by 4 factorial times x to the power 4. So all the fours. The next term would be the fifth differential when x is 0 over 5 factorial times x to the power 5, and so on. So we can find these terms. All we have to do is find out what these are. So that's Maclauren series. It's a way of writing a function as a power series to help us differentiate or integrate a function. So let's have a look at it in action. And here's an example that I've written out for you. Determine the four terms of the power series for cos x. So our function is cos x. So what we're going to do is, for this function cos x, we're going to find the first differential, the second differential, the third differential, the fourth differential, and so on. And often with these things we find we end up getting a pattern, so we can then continue. For each one, we're going to find the value of the function, or the first differential, or the second differential, when x is 0. So you differentiate and then you let x equal 0 and work out what the answer is. So let's see how it works in this table. So what we do is, our function is the cos of x. So the first thing to do is, what's the value of the function when x is 0? What's the cos of 0? The cos of 0 is 1. So our first constant is 1. Next we differentiate. What's the differential of cos x minus sine x? And the table differentials. Once we differentiate it, we find out the value of that differential when x is 0. What's minus sine of 0? 0. Then we find the second differential. What's the differential of minus sine x? Minus cos x. What's the value of that? When x is 0, minus the cos of 0 is minus 1. Differentiate that, we get sine. Differential of sine is 0. We start to see a pattern. Look, it's going 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0. So we can now put those into Maclauren series, which is down here. There's Maclauren series, written out. The value of the function when x is 0, the value of the first differential, lots of x, the value of the second differential at 0, lots of x squared over 2 factorial, the value of the third differential at 0, lots of x cubed over 3 factorial, and so on. So, we've worked out what the value of the function is at 0. It's 1. We've worked out what the value of the first differential is at 0. It's 0, and so on. So we can substitute those in. The value of the value of the function at 0 is 1, so that's this. The first differential is 0, so that's gone. The The second differential was minus 1, so that gives us minus 1 lots of x squared over 2 factorial, or just minus x squared over 2 factorial. The third differential was 0, so that's gone, because that was f3, 3, 0 was 0. The fourth differential was 1, so that gives us this, because that was plus 1, the fourth differential. And the next one was 0, so in other words, we miss out every other one. We just get the even terms, and it alternates. Positive, negative, positive, negative. And that's the power series for the cosine of x. Used by differentiating cos x successively and working out what our value of that is when it's 0, x is 0, and then plugging those into this Maclauren series. And that's it. The only difficulty is when you've got an awkward thing to differentiate. So let's just have a look at an example of one where we've got an awkward thing to differentiate. But before we do that, here are some conditions of Maclauren series. It only works if we can find out what the value of the function is at 0 here. In other words, it's not infinite. If we find that we differentiate, or we try and work out what the value of the function is when x is 0, and it turns out to be an infinite number, then we're stuck. We can't use power series. So many functions can be expressed as power series, but not all. And these are the conditions. The value of the function cannot be infinite at 0. The value of the first, second, third, or any differential cannot be infinite. And the final condition is that as you add terms, it must be convergent. In other words, the terms must gradually get smaller and smaller, because what we've got here is an approximation for the function. So here's a convergent series. Each term is gradually getting smaller. So you can see you're going to converge on a final answer for the function. If these figures were gradually getting bigger, then I'd have to have more and more terms and it won't work. So it must be convergent, and you cannot have an infinite number. Note, log x is one that we can't do because the value of the first differential of log x at 0 is 1 over 0, which is an infinite number. So you can't express the log of x using the Maclauren series as a power series. But you can with a bit of a trick, and Taylor's series that we're not looking at, and if you want to look at it, you can. That will allow us to get around that problem. So here's an example, and we're going to have to differentiate this to do it. So I want to express 2 plus x to the power 4 as a power series. Chain rule. Remember how the chain rule works. Look back at the chain rule. Remember, the chain rule tells us that the differential of the function is we let the inner bit equal u, remember. The inside function equal u, and then we differentiate y with respect to u and multiply by u by dx, if you remember. So, for example, here are some examples. Look, this is the inner function. So the differential of sine 3x is, the differential of sine is cos, but then you multiply that by the differential of the inner function, which is 3. So that turns out to be right, yeah, differential turns out to be 1, doesn't it? So that just turns out to be 1 lot of cos 3 plus x. Differential of this one, you ignore the inner function, chain rule. Differential of sine is cos, so it's cos 3 plus x squared, and then you multiply that by the differential of the inner function, which is just 2x. So that's where the 2x comes from. And you might need to review the chain rule so you can use this properly. Here's another one. What's y equals e to the 3 plus x squared? That's the inner function, if you like. So the answer is going to be the differential of e to the x, which is just e to the x, multiplied by the differential of this, which is just 2x. So Maclauren gets difficult when you've got awkward differentials to do. But certainly in the exam you're not going to have an awkward differential to do. Here's another example down here. So if we did this one, the differential of log x is 1 over x. So what's the differential of log of 1 plus x? It's 1 over 1 plus x, which I can rewrite as 1 plus x to the minus 1. And then the second differential is going to be the differential of that, which is minus 1 times 1 plus x to the minus 2. The differential of that will be minus 2 times minus 1 is plus 2 times 1 plus x to the minus 3, and so on. And here they are. First differential, second differential, third differential, fourth differential. Just pause this and check, if you're looking at the video, that you see how those work. So, all I've got to do now, once I've got the differentials, is to find out what is the value of these functions, and the first differential, and the second differential, and the third differential, when x is 0. So, the first one, the log of 0 is 0. The second one, the first differential, if I let x equal 0, then it's going to be 1 to the power minus 1, which is 1. Here, if I let x equal 0, it's just 1 over 1 squared, which is just minus. So it's, in other words, it's going to be minus 1 for this one, plus 2, minus 6 for this one, and so on. Because in x is 0, all we're left with in here is a 1, so it actually doesn't matter that it's to the power minus 4, it's just 1. So these numbers in front, and in this case it's just a 1, give you these constants. So these are the numbers that you're going to then put into Maclauren. So we put them into Maclauren. Here's Maclauren again, remember. So put those numbers in, and that's the power series for the log of 1 plus x. There. And then simplified, it looks like this. So again, just check you see how it works, work it through. And often when we write these power series down, we can see a pattern forming. And once you see the pattern, you can actually carry on and just write down as many times as you want. So that's the power series for log of 1 plus x. So if I asked you to integrate the log of 1 plus x, it's easy if you write it as a power series, because I just integrate each of these in turn by adding 1 to the power and dividing by the new power. In the textbook, there's a section of the Maclauren series which goes through some examples. In practice, it turns out that it's like to be the sine function, the cosine function, or this log 1 plus x function that you're going to be asked to look at, because otherwise the differentials get a bit more awkward and under exam pressure, and you're going to be asking to do something like that. So in practice, it's going to be one of these basic functions that you're going to look at. And if we look at the exam question, which you had here, you're actually given it, the power function here, aren't you? So, in the exam, I'm going to give you the power function so you can use it to perform the integration, as we were looking at a minute or two ago. But further on in the question, you can then gain more marks by using the Maclauren series that you are given to actually arrive at the power function and talk about how it's